This is Agilent SystemVue, which is the heart of the cognitive radio test bed. Before we get to the live demo today, let's quickly review the test setup. This math language script allows us to select either a mobile WiMAX link or an LTE link. Scrolling down the math language script, we see that the first analysis that is performed is DF-scan environment. And if I open up the schematic that corresponds with this analysis, we see that the schematic consists of an RF sensor source element. This is actually a custom source element, but it allows us to read and capture data from a remotely located RF sensor. In our case, for the demo today, the sensor is located in Western Washington State. This PC that I'm doing the demo from is located remotely in Eastern Washington State. Now, when the simulation is performed, what happens effectively is that we read in the sensor data. It's then stored out into ASCII I and Q data files, which we'll use later on for the mobile WiMAX and or LTE simulation. Now, going back to our math language script, we can see as we scroll down that the next step is to search for white space. And so this function, this math language script, actually calls a secondary function, which I'll open now. And the secondary function basically goes through and it scans the frequency space and it looks for rising and falling edges, and it uses this information to compute the available white space. This is then compared against the policy to determine valid white space. Now, once valid white space is computed, the MathLang script then sets up either a mobile WiMAX or an LTE link. And to do this, it runs several different schematics. If we're running a WiMAX link, this is a schematic that would be simulated. The schematic consists of a mobile WiMAX source. To this, we add the cognitive radio spectral environment using the ASCII files that we had stored out previously. The composite signals then run into a mobile WiMAX receiver, and then this allows us to perform a bit array simulation on the resulting WiMAX link. Likewise, if we were running an LTE link analysis, we'd be setting up the center frequency on an LTE downlink source, which is an OFDMA signal. And again, to this, we're adding the cognitive radio environment that has been stored out in these ASCII files. And then the composite signals run into an LTE receiver, which performs baseband post-processing to enable the coded bit array simulation to be performed on the link. So that's a real quick overview of the demo setup. Let's go ahead and do the live demo. To begin the demo, we'll hit the Go button. This will launch the first simulation, which is a schematic that contains the custom RF sensor link element in SystemVue. We can see that the simulation is completed. We've read the remote RF sensor data into SystemVue, and we can see that the cognitive radio spectral environment consists of two spectral peaks. Now the white space algorithm is running in SystemVue to detect or compute the available white space between these two spectral peaks. It'll then try to determine if a 5 MHz or a 10 MHz mobile WiMAX link will fit, and if so, it'll center it between the two peaks. Here we can see the mobile WiMAX simulation is in progress. And the simulation is completed. We see the resulting mobile WiMAX spectrum, which is centered between the two spectral peaks. Now scrolling down the math language algorithm, we can see that the white space bandwidth that has been detected and computed is 6.1 MHz. And scrolling down a little bit further, we can see that the resulting mobile WiMAX link bandwidth that has been configured by SystemVue is 5 MHz, and so consequently it has centered a 5 MHz mobile WiMAX link between the two spectral peaks. Now let's go ahead and change the link type preference from mobile WiMAX to LTE, or long-term evolution. And again, to launch a simulation, we'll hit the Go button. The process is much the same as the mobile WiMAX demo, but here we're reading the remote RF sensor data back into SystemVue, and now the white space algorithm is trying to determine if a 5 MHz or a 10 MHz LTE link will fit between the two spectral peaks. The LTE simulation is in progress. And the white space algorithm is actually, it'll determine the white space, available white space between the two spectral peaks, but then it'll try to compute whether or not that white space is valid by comparing against a frequency policy, which is shown graphically by the dashed blue line. So here we can see the LTE simulation has completed, and as a result, it has centered an LTE spectrum between the two spectral peaks. If I open up the data set for the LTE analysis, and let's go ahead and bring up bit error rate, we can see that the coded bit error rate of the LTE link is 0%. Now let's change our cognitive radio spectral environment to see how the white space algorithm responds. To do this, we'll change the frequency on a signal generator from 1903 MHz to 1908 MHz. Let's go ahead and change the link type preference back to mobile WiMAX. Let's dismiss the LTE display and rerun our analysis. We can see that the first simulation is completed, reading in the remote RF sensor data, and as a result, this spectral peak on the right-hand side has moved out in terms of frequency, and we can see the additional white space that is available between the two spectral peaks. Now the mobile WiMAX simulation is in progress, and as a result, we see the new 10 MHz mobile WiMAX link centered between the spectral peaks. Now scrolling down the math language algorithm on the left-hand side, we see that the computed white space bandwidth is 11.48 MHz. And then scrolling further down, we can see that the mobile WiMAX link bandwidth as a result is 10 MHz, which corresponds to the WiMAX spectrum that is now centered between the two peaks. If we open up the data display for the mobile WiMAX simulation, we can also see that the coded bit error rate of the mobile WiMAX link is 0%. To learn more about cognitive radio algorithm development and testing, please see Agilent's new white paper at www.agilent.com/find/ESOF Cognitive White Paper. Thank you for your time today.